1, 2, 3. Am I audible, guys? Asset.
মাইক্রোফোন বন্ধ করে দিয়েছি। এমনি অডিও আসছিল, সেটা চিন্তা নেই। অডিও আসছিল, ব্যাকগ্রাউন্ড নয়েজ আসছে, কিন্তু অডিওটাও আসছে। এখন তো মাইক্রোফোন বন্ধ করে
হ্যাঁ না আমি
differentiates physics into the different stratas based on the size of the objects we're dealing with and the speed of the objects as well. So I have color coded all the different fields of physics, roughly speaking, into different sections of this cartoon. So what you see over here is the color coding for atomic, molecular, and optical physics, biophysics, and essentially the condensed matter physics. So if you think that why I have placed it here, it's essentially because biophysics relatively deals with the, how should I say, particles or objects which are visible to mankind in some shape or form within using the microscope and stuff, and as well as for optical physics and experimental condensed matter physics. These deals with scenarios where the objects have a size which is not very less compared to what you would expect in terms of the other fields of physics, which I'll discuss. And also it lies in the realm of classical mechanics because these objects have a speed which is deducible by man. So you can see a guy cycling over here. So this is a speed we're accustomed to. So these topics deal with relatively small speeds and relatively larger objects. Then I have three other fields, which is theoretical and observational astrophysics and cosmology, which deals with extremely large objects like celestial bodies and deals with extremely high speeds, like comparable to the speed of light, as you can see from the green blob here. And finally, I have taken the liberty to place experimental and theoretical particle physics and string theory in the realm where it discusses the fastest and the smallest objects you can imagine. So this string theory position is a bit loosely explained, but this gives you the general idea of the different kinds of physics and the size and the speed that we're discussing over here. But what do I work on? I work on particle physics. So particle physics is basically the study of the most fundamental constituents which make up everything that we see, feel, or experience. So it's like the base of everything. Now, in order to give you a kind of grander picture of how small is particle physics, let's take a look at this chart. So you have the universe. The universe is the biggest observable object that we have seen so far. Then comes the solar system, which is obviously way smaller than the universe, but it's still a huge celestial, I would say, collection of planets and asteroids and satellites and whatnot. After the solar system comes the Earth, where we all live in, but it's still a huge planet in some sense. And then in the Earth, you live, and you are made up of your DNA molecules. Now, when we were kids, we were taught that DNAs are the, kind of biological building blocks of you. But what are DNA molecules made up of? Particles. So you see, everything that you see, it's your laptop, it's your table, it's your friend, it's your food, everything that you see is made up of particles, which constitute particle physics. Now, fine, this is a grand idea itself, but how do we understand what are the particles that constitute this? So yes, it's very interesting, but it's challenging as well. So today we would like to take a look into the deeper details of what the particles are. So according to particle physics, there is a theory called the Standard Model, which postulates that there are primarily two kinds of particles. Fermions, which are matter particles, and bosons, which kind of give you the force. They're force carriers. So first of all, I would like to discuss about fermions. So fermions can be divided into quarks, and there are three generations of quarks, like the up, down, charged, strange, top, and bottom. Now the quarks have some unique features. The quarks have properties like mass, charge, and color. So in your high school days, you have read about charges, but you have always associated it with electrons. So in this case, what I'm talking about is called color charge. So according to a theory called quantum chromodynamics, get confused with the jargon. It's just how we physicists talk. But I'd like to kind of tone it down so that you understand. Quarks are said to possess something called a colored charge with 3 basic colors: red, blue, and green. Now, how you should understand this colored charge is that when we say quarks make up everything we see, we mean that quarks kind of combine with each other in some sense, and they give us the particles which make up everything. So if I were to say that there are some particles called kaons and pions, those are falling under a category called mesons. They will be made by a quark which has one color and an anticolor. So for this example, which I've picked is that the quark has the green color and anticolor quark as well. And these two combine to make particles like kaons, pions, etc. Now, these are a bit more fancy particles, but from our high school days, we all know about the proton and the neutron. So these protons and neutrons are also made up of quarks. Protons are made up of 3 quarks. Neutrons are also made up of 3 quarks. So if you would like to imagine the scenario, these 3 quarks have to be of different colors so that they can combine and make the proton and the neutron. Now, when I talk about colors, you might imagine that how can we actually see colors in these particles? We don't. But I mean, from childhood days, we have been accustomed to associate things based on the color or the nature. And that's why the colored term is taken very loosely in this theory. It's not like we literally see green, blue, or red. It's just a way to imagine things. So this was a basic idea of quarks. And after the quarks, it was also postulated that there is another subset of fermions called leptons, of which I'm pretty sure almost all of you have heard of the electron, the muon, and the tau. But there are also particles called the neutrinos, which origin for each of the 3 generations of the leptons. So the leptons have a charge because we have always studied about electric charge, which comes from electrons. So all the 3 classes of leptons have a charge and they have a distinct mass, whereas all the neutrinos do not have any charge. They are neutral charge particles and almost massless, not exactly. So again, as you see the beautiful arrangement, the leptons are also arranged in order of masses. So if you take a look closely, you will understand that the electron is the lightest lepton, followed by the muon and followed by the tau. So that is how the generations of leptons are organized by their masses. And finally, apart from the standard electric charge that we know of electrons at least, leptons also possess an intrinsic rotation. It's kind of like an idea, which I like to think as an idea. So they have a change in rotation in their spin, which kind of helps them generate magnetic field as well. So we know that from our high school level studies that electromagnetism is a fact. And so that way we can mention that leptons are able to interact with other matter only through weak electromagnetic forces. So now I've discussed about the fermions, which are the matter particles. But the exchange or the interaction of these fermions or leptons, they depend on something called the bosons. So the first one I'd like to talk about is the gluon. So the gluon basically carries the strong force. So what I mean by this is that the gluon is the force carrier for interactions between quarks. Followed by that, we have the photon. The photon is probably the most common particle because you can see it in your day-to-day lives as light. So photon constitutes of light. And as the nature goes, it carries the electromagnetic force, which is an interaction between the leptons. And finally, we have two or let's say three gauge bosons. So these are vector gauge bosons, which are responsible for the weak force. So leptons interact with these as well, these three force carriers. Now, I have discussed the strong force, the weak force, and the electromagnetic force. But if you remember your high school days, you have always been taught that there are 4 forces, and the 4th one is gravity. But I have not placed it here because even though we are all experiencing gravity every day, we have not discovered conclusively the particle which kind of contributes to gravity, if at all. So that's why it is not there in the standard model of particle physics. Now, after learning about all these particles and the force carriers, one question might pop up in your mind. Fine, these give mass and matter to everything, but how do these particles get their own matter? The answer is the Higgs boson. So the story is that the Higgs boson is supposed to be giving mass to all of these other particles. So it's kind of like the mass giver for the standard model. Now, I would like to imagine the scenario. I love to imagine the scenario that's how I was taught about it in the first place, that you can think of how the Higgs boson interacts with the different particles like this. Let's say you're in a room and the room is empty. You want to walk from one side of the room to the other side of the room. You can walk easily. Now let's say the room is filled half with water. So it's a bit more difficult than just walking. You have to almost swim across to the room. And now finally, let's say that the room is filled with honey. Then it's much more difficult to cross a room filled with honey rather than just walking across. So when you think of the 3 scenarios, room without water, with water, and with honey, this basically tells you that if the honey or the water is the Higgs field, how much a particle interacts with the Higgs field gives the mass to the particle. So in this case, from the standard model of particle physics and from observational experiments, we have seen that the top quark interacts the most with the Higgs boson, and that's why the top quark is the most massive particle in the standard model. So, and the other quarks and the leptons, they interact lesser with the Higgs boson, so their masses are smaller than the top quark. So all these particles, except for the Higgs boson, were discovered mostly in the mid to late 1900s. But the Higgs boson was discovered very, very recently, less than a decade ago, at the Large Hadron Collider at CERN. And it was jointly confirmed by both my experiment, ATLAS experiment, and another associated experiment called the CMS experiment. Now, what you see over here is an animation of how exactly 2 protons collide with each other inside the ATLAS detector, and there are gazillion particles forming and coming out of this collision. Now, the challenge is to understand what's coming out and how that is. So it's a complicated study, and to understand what exactly is happening in this collision, I would like to discuss the nature of the ATLAS detector itself, as in how we understand what all these lines are about. So what you see on the left-hand side is the generic structure of a detector, or rather the ATLAS detector itself. So over here on this side is something we called in the generic terms as a tracking system. So the task of the tracking system is to take note of particles which have charge. So it records the tracks of charged particles. So what you see over here in the tracking system is that the muons, it has charge, so it has a path in the tracking system. The photon, since it is chargeless, it is invisible in the tracking system. So you see that the dashed line over here, it represents that there is no contributions from the photon to the tracking system. You do not get any energy changes because of the photon. Similarly, for the neutron, since it doesn't have any charge, you do not get any effect of it in the tracking system, but you do get it for the electron. Now, after the tracking system comes the electromagnetic calorimeter. So when I'm talking about electromagnetic calorimeter, it obviously means that I am recording information which has electromagnetic interactions. So obviously it's the electron in this case. So the electron deposits all of its energy in the electromagnetic calorimeter and it's done. Then after the electromagnetic calorimeter comes the hadronic calorimeter. So the hadronic calorimeter mostly deals with quarks in the loose sense. So what you see over here is the proton depositing its entire energy within the hadronic calorimeter, and the neutron as well. It deposits its entire energy in the hadronic calorimeter. Now finally you see a yellow or orangish line. This is the muon. The muon is the most long-lived standard model particle, which means that it does not decay to other kinds of particles as fast as these particles I just talked about. So the muon travels all the way through the detector and leaves its trace in something called the muon spectrometer. So this system of the detector is specifically built to record muons. Now you might notice a white dashed line on the right hand side. This white dashed line is the neutrino, because neutrinos are chargeless neutral particles. They do not interact with anything in the detector. So they just walk away, and technically we do not see anything that happened associated to a neutrino. But then how do we understand where the neutrinos are in which physics processes? We understand by the simple idea of energy conservation. So if you remember your high school classes, there was this concept of energy before collision has to be equal to energy after collision. So that's the same principle we apply in looser terms, because I'm explaining it in a much more generalized manner. So we apply this energy conservation principle. And if we see that the energy of the particles before the collision is not equal to the total summed energy of all the particles after the collision, then we say that fine, there's something missing. There is a missing energy, and this missing energy is coming from the standard model neutrino particle. So once you've understood the left-hand side of the picture, which basically gives an overview of how the different different particles behave, the right-hand side of the picture basically is called an event display. So what you see on the right-hand side is contributions to two portions of the hadronic calorimeter. So this is something we called a dye-jet system, which I will explain in much more detail later on. But this is how we like to picturize our experiment or particle collisions within the experiment. So yeah, I mean, and that's how we kind of understood the Higgs boson discovery. So on the right-hand side, what you see is a very beautiful plot. This shows you that what we would have expected from standard model is this red region. But you see that there is kind of a lot more collection of data in this region which is unexplained. And this blue region, which is the unexplained data, was the Higgs boson. So when it was discovered back in 2012, I was a high school student. I was in my class 12th, and I didn't know much about it at all myself. But I was keen on particle physics by then, and I did some digging and read a few articles. And then I was mesmerized because there was just one thing that all the scientists within ATLAS and CMS experiment were saying. They were saying that we found the Higgs boson, and it's like finding a needle in a haystack, because there's like a gazillion events where the Higgs boson is not there. You have to dig through those events and find that one event where you find the Higgs boson. So yeah, but after 2012, this Higgs boson discovery, have we understand everything? No, we still don't have all the answers. So at this point, I'd like to take a short break because we had discussed this will be more of an interactive session. So if you have any questions at this point about whatever I discussed, I will be happy to answer them before moving on to the next portion of my talk.
Yeah. So, hi everybody. This is Geneva from Project Cantilever. So now we will take some questions and we will forward them to Sukanya. And if you have any questions and doubts of whatever Sukanya has presented till now, you can go to the chat box and ask.
I'll try to see if I can see the chat box. Looks like I can.
Can you see it, Sukanya? Because
yeah, I can see the chat box.
Okay, okay, that is. I think Satvik was asking something about, yeah.
Okay, flavors of quarks. Right. So let me go back to my presentation. So these are the 6 flavors of quarks. So up, down, charm, strange, top, bottom. So these are called flavors of quarks because they have slightly different properties, but that's the general idea. Did I answer that question properly, Satvik? Or do you have any more doubts before I move on to the next questions? Okay, so I see the next question is from Annie. Okay, so this is an interesting question for the W boson, why both positive and negative charges. So if I may go through this presentation. So the W boson has a positive and negative charge because of the Yukawa coupling calculation which you have in the CK matrix. I mean, I would have loved to explain this in more detail, but I cannot without doing proper calculations on the board. So I could suggest some references which you could use for the sign of the W boson, but I mean, in a general sense, it has to deal with the couplings that you have in the standard model. Then I have the question from Ashwath. Confirmation of the Higgs was done by ATLAS and CMS. What did this confirmation consist of? I mean, was it fundamentally different from the discovery at LHC? Oh, no, ATLAS and CMS experiments are part of the LHC, the Large Hadron Collider. So if I can go back to the picture I had initially, yeah, so the Large Hadron Collider is this huge collider underneath the border, underneath Switzerland and France. And within this collider, you have the different experiments: ATLAS, ALICE, CMS, and LHCb. Now, ATLAS and CMS roughly have the same kind of structure, and they try to look for same kind of particles, whereas ALICE and LHCb tend to look for a bit different kind of particles. So when I say it was jointly confirmed by ATLAS and CMS, I mean that researchers did their study in both the experiments almost simultaneously, and they almost simultaneously published the findings. But it's all within the construct of the Large Hadron Collider. Both the experiments take the same data from the Large Hadron Collider as ALICE and LHCb as well. So
yeah, okay. So Sukanya, I think we should move on, because like questions will keep on coming.
yeah.
So, yeah, we can. What we can do is that when you finish, after that we'll keep a 10 to 15 minutes time for questions.
Mm-hmm. Sounds good.
Okay.
Okay, then I should move on. I was here. So getting back to the main talk, this is kind of a chart which says what are the key particle discoveries from the early 1900s to what happened till 2012. So now I would like to discuss with you about something which is happening now. So even after the Higgs boson discovery, do we know everything, or are there questions which are still open? Yes, we do not know everything. There are questions like, what is dark matter? What is time? Why are we just moving forward in time, and why can't we just move backwards in time, or rather do time travel? And apart from that, there's also this question which is kind of famous between conspiracy theorists mostly: are we alone in the universe? Or are there any other species out there, probably way smarter than we are, and they're far away from us? So are there any other alien species out there? And finally, if you have heard about cosmic rays, so this is also a question that who is shooting cosmic rays towards the Earth? Why do cosmic rays fall on the Earth? And there are several other questions in other fields of physics as well. But as a researcher, you can only do so much in one lifetime. I wished I had like a gazillion lifetimes to try and solve all of these questions. But unfortunately, since it's just one lifetime, my research kind of is involved with dark matter. So what is dark matter? Astrophysical studies have said that celestial objects like stars, as you can see here, or gas clouds or galaxies, they kind of move faster than they would have if they only experienced the gravitational force of other celestial objects, which means that there is some extra force which is being imparted on them, which we do not know of. And that we call dark matter. So calculations done from astrophysical and cosmological information has told us that everything that we see or experience, that is you, me, this whole world, it's just roughly 5% of the total universe's matter content. The rest of the 95% is made up of dark matter and dark energy. But do we know what that is? No. So the general question is, we need more physics to understand what dark matter and dark energy is. And that's what I'm exactly doing at the ATLAS experiment at CERN. I am searching for dark matter using the Large Hadron Collider data. But what is dark matter? To understand this, you need to have kind of a historical development of the concept. Even though I'm a physicist, I love to learn about the history of how the theory came about, because it helps you give a lot more insight into your existing work itself. So I'd like to start with the story of dark matter, which starts way back in the 1930s, when Fritz Zwicky studied the redshift of various galaxy clusters, and he noticed that there is a large scatter in the velocities of the different galaxies in the Coma cluster. And he calculated the mass to light ratio, and turned out that that ratio was very high. So this pointed to the existence of dark matter in some shape or form. And he called this donkey mattery, which basically translates to dark matter. Now, that was a big hype in the 1930s itself and went throughout the 1940s and 50s. In the 1960s, there was this new idea. People said, maybe we can look at dark matter from the standard model perspective. And then if we look at dark matter from standard model perspective, we say that, fine, maybe neutrinos are a dark matter candidate because they do not interact with any other particle. They supposedly do not interact with the detector material. So maybe they are a candidate of dark matter. But neutrinos could not have been dark matter because then you would not be able to account for the large scale universal structure which has been contributed by neutrinos. I mean, you have heard of neutrino stars and stuff in astrophysics courses probably. So yeah, I mean, neutrinos essentially cannot be a dark matter particle. Then we wouldn't see so many large scale observable universal structure. So that was that. Neutrino was obviously out of the question. And then finally, in 1970s, this idea came about that physicists started to consider the possibility that there might be a space-time symmetry in nature, which kind of relates the fermions and bosons, as I was talking about a couple of slides back, and they call this theory supersymmetry. So they said that according to supersymmetry, every standard model particle should have a supersymmetric partner. And they predicted that the supersymmetric partner of the neutrino, termed as the neutralino, can be a dark matter candidate. So supersymmetry was a theory which was postulated back then, and it just grew in hype and popularity, and a lot more physicists started discussing it every day and other day. And till date, there are theorists who have devoted their life to supersymmetry and understanding how this beautiful theory is behaving. So then that was another suggestion for a dark matter candidate. After that, in the 80s, came the theory that there might be something called an axion. Now, in order to understand the axion, you need to have a proper particle physics course. So I will not go into the gory details of how an axion is formed, but it came as a natural solution to one of the long-standing problems in particle physics called the strong CP problem. And it was postulated that maybe axion can be a dark matter particle as well, which if we find it, it will resolve this problem within particle physics. And then finally, in the late 80s and 1990 onwards, there was this idea that maybe since the dark matter does not interact with anything, obviously it is weakly interacting, but maybe it's massive itself. So they came up with the idea of weakly interacting massive particles, WIMPs. And from this idea of WIMPs came a plethora of studies which have been done with dark matter particles postulated as WIMPs. And I mean, over the years since 1990s and up till Atlas and CMS was designed, there has been gazillion papers which have been discussing different types of dark matter particles and how to kind of probe dark matter, because that's one of the long-standing questions right now. It's definitely there, but we don't know what it is. But yeah, I mean, even after, I would say, almost 16 or 17 years since ATLAS was kind of conceived and designed and found the Higgs boson, we still do not have an answer to what dark matter is or where we should be looking for dark matter itself. So thinking of all those things, what am I working on at the moment? So I'm trying to look for the dark sector showering using semi-visible jets. Right. So that sounds confusing. So maybe let's just take a step back and try to understand what these semi-visible jets are. So previously, if you remember in the first section of my talk, I was discussing about something called a dijet system. There was this colorful animation with the circular object, and you had two lines up and down. That was a dijet system. But what are jets in general? Imagine you have a pizza. Now, if the base of the pizza is considered, then the toppings are the particles. And this pizza, when you constitute as a cone, is called a jet. So a jet is basically a conical collection of particles within a certain radius or a certain phi range. Now, I am looking for jets where some of the particles are missing. So I have some particles present inside the jet and some particles which are missing. So that's what I'm searching for, and that's why the simple term of semi-visible jets arise. So you would ask, how can I see or understand what semi-visible jets are? That would be a good question. So again, we will come to the basic principle that we all have learned in our high school physics classes. Total momentum before collision has to be equal to total momentum after the collision. Now, in my case, if I see that there is a difference between these two values, then there is definitely missing energy, which may be dark matter. So that's the general idea. And I mean, I have toned it down in very simple terms, because I mean, practically, I don't just take the momentum before collision and just subtract it from the after collision momentum, and that's it. That's my research. That's not it. But it's a simple idea for everyone to be able to imagine how we particle physicists are trying to search for dark matter. But fine, that's what I'm doing right now. But how did I get here? So I started out as a bachelor student, like a lot of you in the meeting, I presume, at the Calcutta University, and I did my bachelor's from Ashutosh College, which is in fact the alma mater of some of the Project Cantilever representatives as well. And then I did my master's from Banaras Hindu University back in 2016. I started my master's, and after that, I finished my master's in theoretical particle physics. So whatever I discussed so far was experimental particle physics, but I had no idea what that was when I finished my master's. I did my master's in a completely different module of particle physics, and I didn't know how experiments were conducted or how we study anything that we see in the detectors. Then I applied and I got offered the position to join as a doctoral student in the ATLAS group of University of Wits. And the picture you see here is me inside the LHC tunnel. I was really lucky to have been there before the pandemic, and I got to see the entire LHC tunnel. So it's always nice to see where the data is coming from, which you're looking at day to day. So that's there. But I mean, when I'm talking about a career as a particle physicist, I can never end the conversation by just saying the pros of being in the particle physics business of some sort. So I would like to place a pros and cons scenario for you, because I mean, if you're excited after listening to the talk, which I hope you are, then you should know what you're getting yourself into. So the pros of being a particle physicist, or rather a physicist in general, is that you get to be a part of cutting edge research. This is like the biggest experiment mankind has made so far, and you get to kind of delve into the deeper questions that nature works in mysterious ways, and you try to understand how the deeper questions have meaning. You get to meet brilliant researchers who have devoted their entire life to understanding the intricate details of particle physics. And finally, if you become an experimental particle physicist, there are chances that you will be traveling a lot. I mean, I am coming to you live from airport hotel in London Heathrow right now, where I am sadly having to quarantine for 10 days because I traveled. But ever since I started my PhD, I have traveled to roughly 7 countries outside India, and I love traveling. So this is definitely a plus point for me. But on the con side of things, you must understand that research is challenging. It's not like you have a definite answer to a problem. You might be working on a problem for years, and then you realize, oh, it was not worth it. Someone has solved it in a different way, and that's much more elegant. Or maybe you realize midway in your research that, oh, maybe this is not how I should have done it, and this is a dead end, so I'll have to start again. So research is very challenging. You do not know what the end outcome will be. So if you're kind of ready to take that challenge, and you're willing to understand how the universe works, and if you ever had the question how particles which are unknown to our eyes, but they make up everything which we see, and if you ever thought how do things happen as they happen, then maybe this career path is probably for you. But in the end, it's your decision whether you would like to be a particle physicist or not. So yeah, thank you for the time, and I hope you have more questions.
Yeah, thank you, Sukanya, for this wonderful talk. We are very pleased, and we have got to know a lot of things. So today, now we will have the question and answer session. But before that, let me just give a small introduction of Project Cantilever, because till now I haven't given it. So the idea of Project Cantilever is to create a bridge between students and researchers, to inspire the future researchers with the help of today's researchers, brilliant researchers like Sukanya. And the coordinator of today's meeting is Akash. And it is very, this is where the date of today is 28th of February, and we all call it the National Science Day, because in 1928, C.V. Raman gave his brilliant theory of Raman effect on the same day. And Akash has done his MSc from IIT Kharagpur, and he belongs to the same institute in which C.V. Raman used to work. So he is from the Indian Association for the Cultivation of Science. And so that's it. Now I will go to Akash to coordinate the doubt clearing and the question and answer station. Thank you.
Yeah, thanks Agniva, and thanks Sukanya for this lovely talk that you gave. So right now, what I will do is that I will just tell you the timeline from now, because we don't have a lot of time. We have 10 minutes. So what we will do is that we will take few questions from the student who are present in the meeting, and also we are live broadcasting it over YouTube. So from there also we'll take 1 or 2 questions, and I know that there are a lot of questions because the topic is very interesting. So if all your questions are not answered, we will give you a feedback form wherein there will be a portion where you can submit your query, and we'll address it later on. Okay. So Sukanya, you can start taking the questions now, because I think the students have already started, posting the questions.
Yeah, I think if you can read the questions out to me, it will be easier for me to go to the next slide.
So, yeah, the first question is from Subaida. So the question is, LHC accelerates particle to very high speeds so that they collide and hence provide valuable information. So as these particles are very small, how do you align them in the LHC to ensure that they perform successful collision?
That's a very intelligent question. So as she said, the particles are very small. So since we are colliding protons and protons are charged particles, we use superconducting magnets to align the protons and kind of make them go in the direction how they should be in order to collide. But then again, having said that, I would like to mention that out of the protons that we generate for the collisions, not all of them collide, because it's like if you try to imagine the collision of particles, it's like one person is standing at one end with a gun and the other person is standing 10 kilometers away with another gun, and they both shoot and expect that the bullets interact with each other and hit them from 10 kilometers apart. So it's very unpredictable. That is why we use high-tech magnets and superconducting systems to control the direction of the protons coming together. But then again, we do not have 100% collision rate in most cases. And it's still an amazing feat that we are able to collide such small particles with such high energies just by using our existing knowledge of electromagnetics in some sense.
Yeah, so I think that was lovely answer. So I'll take one more question from the YouTube channel. So Aniruddha Mukherjee, she's asking, how do you apply to CERN to do your postdoc over there? And also, how did it feel going there?
Okay, yeah, so this is a question very close to my heart, because ever since I was a high school student and I learned about the Higgs boson discovery, it was my dream to go to CERN and work there. So when I actually accomplished it back in 2019, it was like my biggest dream in the world came true. So I don't know what her field is, but I would assume she's doing physics in some shape or form. So I would suggest, if you are interested in particle physics, you should pursue courses which are relevant to particle physics in your master's level, if you haven't already. And once that's done, you can align yourself to be a particle physicist by applying to different institutes where you have these groups like Atlas, CMS, ALICE, or LHCb. If you join one of these groups and your PhD advisor is a member of these groups, then technically you get to become a part of the collaboration itself. And as for postdoc at CERN is concerned, CERN has a few fellowships which it provides to brilliant researchers, whether in particle physics theory or experiment, every year. But it's a highly competitive process. So you need to have a very strong CV. And since I'm not a postdoc myself yet, I don't think I will be the right person to give you tips on how to become a CERN postdoc. But the general idea is you have a strong CV, you have relevant research experience and have significant contributions, and then you apply to this fellowship called CERN Fellowship. And that's how the general steps should be.
Yeah, so thanks for the answer. I think it was lovely. And so there is, Satvik is asking, could you suggest any book for particle physics?
Yes. Do you specifically mean theoretical or experimental?
Yeah, Satvik, you can just unmute yourself and ask.
It could be any of them because I'm interested in both of them.
Okay, so for theoretical particle physics, I would suggest you read Halzen and Martin. That's a very standard book, and I'm not sure which study level you're in. Are you in MSc or bachelor's?
I'm just doing my bachelor's.
Okay, fine. So since you're doing your bachelor's, I would suggest you can start out with Halzen and Martin once you have learned relativistic quantum mechanics. Then it's much more easier to understand that book. And apart from that, there is an experimental particle physics book, which I'm shamelessly promoting because my PhD advisor has written that book. but it is an amazing book, and it's an introductory book for anyone who's interested in experimental particle physics itself, because most of the particle physics books just deals with the theoretical aspect, not the experimental aspect. So when I started out, I started by reading that book in this field, and it really helped me a lot. So if you want, I can share with Akash and Oknibo a few links for relevant books which I found helpful during my studies, and maybe they can spread out the word to you guys.
Okay, there is another question. So the question is, can you please let us know if any aspects or concepts of string theory are being applied in LHC experiments?
Okay, so I'll give you kind of a biased answer because right now, no, none of the concepts of string theory are being applied to LHC because we cannot reach that high energy scale. LHC has been dealing with 13 tera electron volt energy scale and is trying to promote to 14 tera electron volt energy scale for the run 3 of LHC, which is upcoming in 2022 onwards. But string theory basically deals with objects which have energy scales of 100 TeV and more, at least. And probably more than that. I'm not a string theory expert, but no, right now, none of the concepts of string theory are being put to use at the LHC, sorry.
Okay, Sukanya, so I'll just take a final question from YouTube. And so the question is, Oyon is asking that why do we not accelerate a particle at 100% the speed of light at LHC?
They are accelerated to comparable speeds of light, but I'm not sure I'm the right person to answer this question because this is much more of a hardware-oriented question, whereas I am much more of a software-oriented person. But if you would allow, I can look up the answer and let you know it via the feedback form or something, because I wouldn't want to answer something which I'm not 100% confident about. But I can get back to you with that.
Yeah, I think like being a theoretical physicist myself, of course, there are technical, obstacles where you're accelerating particles to huge speed. But even theoretically, 100% cannot be achieved because that is what Einstein said in his relativity, that you can go up till like 99.99%, but you can never reach 100%.
Yeah,
like only light can travel at that speed. Yeah. So that's that.
Yeah, I mean,
okay,
if you do that, it would be amazing. It would break a lot of laws itself.
Yes, of course. Okay, so I think that's the question and answer session. So I know there are a lot of questions among students. So what we will do is that we will post a feedback form in the chat section, and I'll urge the students to submit those forms. So you can also submit the query. There is a provision inside the form. And the last thing that I want to say about Project Cantilever is that right now what we are doing is we are trying to organize seminars like the one we had just now. So apart from that, we are also providing courses on these subjects. So right now we are working with astronomy and space sciences, and in future we wish to bring a lot of other courses, the like real life applicable courses. So yeah, the students can get updated. We'll share our website in the comment section. So I think the feedback form has already been submitted. So just before students leave, just click on the link so that you have it saved in another tab, because when the meeting gets over, you lose the link.
Okay, Project Cantilever. Hello? Hello?
Yes, ma'am. Yes,
Yes.
ma'am. You're audible. Yeah.
On behalf of IEEE SP KMCT CE, I would like to thank thank Ms. Sukanya Sinha for this very informative session, and it was very interesting. And I would like to thank Project Cantilever for organizing this session. Thank you so much.
Yes, ma'am. Thank you.
Thanks for having me.
Yeah, sure.
Thank you, ma'am. And I would like to thank all the participants as well for joining us.
Absolutely.
Thank you. Thank you, sir.
Okay. So, ma'am, then I think we can conclude now. And I think
Yeah.
students have already, submitted or at least clicked the link. So,
Okay.
yeah.
So I call Nija. Nija, are you there? Can you give the vote of thanks? Nija?
Yes, ma'am. So, thank you very much for such an amazing and wonderful session. On behalf of my college, I extend a hearty thanks to our chief guest, Ms. Sukanya Sinha, and everyone behind her who spared time from their busiest schedule to grace this occasion. Also, I would like to thank each and every one of you for actively participating till the end. Thank you all.
Thanks. It was lovely meeting you guys virtually. And
Thank you,
have a
everybody.
nice rest of the weekend.
Okay, then I think we can conclude and leave now. So, yeah.